All right, here's what I want to do today. I want to do one of those days, phone stuff needs to be all completely away. We're going to go through a few things, nothing new. What I want to do instead, I want to take kind of a chance to look through some of the problems you guys have had a chance to work on and give you a little bit of extra information, maybe answer some questions that have come up, et cetera, et cetera. And so I know, and I understand. You guys are anxious to get to the lab and work on things. I get that. I purposely have designed the class so as much as possible, it's hands-on and you're doing that stuff. But I don't want to fight this battle. This is a day when I need to take advantage of a group setting and go through a few things where I'm getting the same questions over and over again, understandably. And I don't want to answer the same question 38 times.
Please come to the office. Kyle Teeter, please come to the office.
And when I do, then that means I'm not available to answer other questions. So there's a reason for this. Okay, so I want to take just a quick look at the 8.2 and 8.3 stuff. And I have added 2 new short assignments to section 8.3. Oh, both of them are only worth half of a normal assignment grade. One of them is, I think it's 16 multiple choice questions that are just kind of things like this, for example. The answer that you provide will be either sometimes, always, or never in each case. What's the answer to this one? 2 triangles are blank similar. Sometimes, always, or never. Sometimes, because they might be, but they might not be, right? So that's what you'd fill in. That assignment does have penalties because it's multiple choice, and so you could just, I want you to think about them. And then the next one, the third part of 8.3, is only 3 problems. They're a little bit more involved, but not that big a deal. We'll look at one example today, and those are going to be ones where you have to do some calculations and come up with some algebra equations and solve. And those are only 3 of them, but I want you to get a little extra practice. Okay, so let's look at 8.2. There's some questions that came up in 8.2. Like, for example, that guy right there. That was one
that was tricky. I gave up on it.
Okay, I'm not gonna lie, I didn't really like 8.2 because of the problem.
I didn't like 8.2.
I'm pretty sure everybody in every class is doing the same thing. Because like my checkboxes weren't loading.
Yeah, and that's right. I understand that. Those are. I think those problems are almost resolved. It's going to be. I don't know. Maybe a couple days. I'm hoping. I've got some information now that I can talk to the people at the ESD about. So that's. I get that. It's frustrating to me too. But I don't want to. Here's what I don't want to do. I'll just give you a quick answer to that. Nicholas, you got to put that away. I don't want to just bail on these questions because they're such good questions. I mean, they're way, way better than the old Moodle questions. And I really want to start kind of replacing the old ones with these better ones that force you to do some thinking. I want you to put that phone away, though. Well, still, I don't care. I don't want music out either. I want those put away. I know this. We're going through experiencing some issues with a few bugs, but it's going to be, think of it this way, it's just a matter of a couple days of dealing with some, and it's not doing it at home, right? Right, it's only at school, and it's just a matter of some district settings on our server, and that's, we'll get them fixed. I promise we'll get them fixed. It won't take long. But then the payoff is we get to use them forever. We get to use them for the rest of the year, and I want to be able to use them in my classes next year, and so on. Yes, ma'am. Yes, you may. You bet. So I apologize in advance for that. I know there's still going to be probably a few days of some issues with that. What I can tell you is it's better to use Firefox at school at least. And once you've loaded up a quiz, so what you want to do is get in and get logged in and get the thing loading, at least for now, ASAP. Because once it's loaded up once correctly, then it works great. Once it's gone through that routine of somehow okaying the answer boxes, then every time you pull up a new page, it should be fine. It's just that first time is kind of a bad one. Okay, but so now what do we do with these? Let's look at this guy right here. Okay, hey, don't talk. Distraction. Okay, so so what about this now? If I want to come up with this, what is this saying here? I want you to think about these. I want you to understand how these problems are structured and what they're trying to ask. What mathematical principles and concepts they're dealing with. If this is true, so we're given this proportion, this ratio equals that ratio, then this ratio equals something predictable based on this first ratio. Now, is it going to be equal to some part of this first ratio? No, it's not. 33/19 is different than both sides of that original proportion. Both ratios are different than 33/19. Neither one of those is equal to 33/19. But 33/19 is equal to some other ratio that we should be able to predict from the first proportion. Okay, does anybody, first of all, can anybody tell me what is the property that we're using here in this problem? You fill in the blanks. I'll start it and you finish this. Here's the property. If A over B equals C over D. So if we have some initial proportion, then what equals what? There's lots of different properties of proportions that we could fill in blanks there and have it be true. But I want the one that applies in this particular situation.
A prime. I think you go C and B.
Janelle, what do you got?
A plus C over B is equals.
Okay, something like that. It's A plus B over B equals C plus D over D. Okay? Now, what did we do there? Okay, all we did is, this is kind of how you could say this property. If A over B equals C over D, or if I have some initial proportion, I don't even have to specify that, I can add the numerator of both sides into their respective denominators. I mean, other way around. Sorry, I said that backwards. I can add the denominators into their respective numerators. So whatever's on the bottom, I could add up into the top. I get A plus B on this side and C plus D on this side, as long as I keep the same common denominators. That always works. That's a property of proportions that is useful to us sometimes, like in this case, right? So in our case up here, instead of A's and B's and C's and D's, what have I got? Well, I've got X's and Y's, but I've also got 14s and 19s, right? So do you see that in this situation right here, the top problem is a specific example of this property where A is equal to 14, right? You see that? 14 is occupying the place of the A. B is equal to 19. C equals, no, X. D equals Y. Okay, so then what does this become? So A over B equals C over D becomes A plus B. What's that going to be?
33.
Okay, so it's 14 plus 19, which is 33, over 19. Okay, what about the other side? See that? Okay, you guys can't talk about this stuff now, though. That's last warning. You gotta go take those desks out there. Okay, does that make sense? Okay, so then the answer is just, what do I fill in the blanks with?
The Y.
That stuff, right? Yeah, good. It's gonna be that stuff. So this is just 33 over 19 would equal whatever. I don't know what X plus Y. We don't know what they are, but X plus Y over Y is what the answer would have to be.
So that would be what you put it to.
That's what you put in, right?
Yeah.
And you could use that fancy little fraction template for that. Okay, good. Moving on. Okay, there wasn't a lot on this assignment, but I think there was maybe.
I needed help on like the whole mean.
Oh, yeah, geometric mean. That's the other thing I wanted to do. Geometric mean. And I've got something really important to show you about this. Geometric mean is something that you will encounter again when you end up doing, there's several parts of math that use this concept heavily. One of them is when you start doing sequences in series, which if you go on in math, you're going to do a lot of. Geometric mean is part of what's called a geometric progression. And so we're not going to talk about that now, but I do want to focus on the geometric mean portion of this. Let's look at this example right here. How about that? This guy. It's a good one. The geometric mean of 16 and 28 is what? Now, who remembers what's the formula for geometric mean?
Shoot.
What do you think? Casey, what is it real quick? I see your hand. Go ahead.
X equals 16, 8
Okay, almost. What do you want to add to that, Danielle?
the square root of 8.
Okay, good. The square root. If I want to find the geometric mean of two numbers, the really short, quick, sort of formula way of doing that is it's equal always to the square root of their product. Okay, that's always going to be the case. You're probably going to forget that. That's something that you don't use it enough that you'll remember that. I want to show you a way, of sort of a real visual way, and written as a proportion, that you can always remember what a geometric mean is, and then solve for it. Very, very simply. Do you remember what that is? Go ahead. Yeah. So we want to write a proportion here involving the geometric mean, and let's go ahead and call the geometric mean. Being as that's what we're trying to solve for, and that's an unknown, let's call it x. How about? Call that x, and then we want to find the geometric mean of the numbers 16 and 28. Here's how we can always set that up. The geometric mean, if I set up a proportion, so I got a ratio on one side or a fraction on one side and a fraction on the other side, right? I know that the geometric mean has to be in the denominator on one side and the numerator on the other side. And honestly, it doesn't even matter which way. I could have written the x on top here and the bottom there, and it's fine. It doesn't matter. Where do the numbers go? The other spots. One number on each side of the equation. The 16, if the 16 is in the numerator, then the 28 is going to be in the denominator. Now, that's kind of an easy thing to remember, isn't it? I mean, that's visual. That's an easy thing to see, that the geometric mean in a proportion is just there. It's just diagonally opposite itself on, on one side and the other side of the equation, right? Now, how do we solve that? How do we solve a proportion? Cross multiply. And so if we cross multiply in two quick steps, we're right back to the formula that we otherwise would know. So x squared equals 16 times 28, right? And then how do I solve for x? Last step? Square root. Okay, so I get x equals the square root of 16 times 28. Now, what if I multiply that out? Obviously, I can do that. I could say x equals the square root of 16 times 28, and I could turn that into a big number. But then if I do that big number, but if I turn it into a big number, then what's the problem with that?
You get different numbers that you would.
Okay, I got to simplify it, and it's hard to simplify a great big square root like that. Now, what does it mean to simplify a square root in the first place? Let's just remind ourselves. I think we've talked about it a little bit. But if I want to simplify a square root, like for example, if I have the square root of 32, that's not simplified. What do I have to do? Hey, put that away, and I can't have you talking. That bothers me. Square root of 32. Okay, I could turn it into 8 and 4, but 32 isn't going to work because I can write that in a simpler way. And by simpler, what's the hardest part? Here's a way to remember this. What's the hardest part of a radical? What's inside the square root or the regular number that's outside? The inside part, right? The square root part's the hard part, right? I want the inside number to be as small as possible. I don't want to have a great big number inside the radical. Well, how do I get it outside of the radical? The only way I can do that is by breaking up that 32 into some factors where one of the factors is a perfect square. Like the square root of 4 would be 2. The square root of 16 would be 4. The square root of 100 would be 10. Right? So I got to find a perfect square that divides into 32. well, someone suggested 4 and 8, right? 4 is a perfect square. So I could split that 32 up into 4 times 8, right? I want to write the perfect square one first, by the way. That's a really good habit to get in. And then I'm going to write that as the square root of 4 times the square root of 8. So 2 separate square roots. The square root of 4 becomes 2 times the square root of 8. Now, are we done with the square root of 8? Is there a perfect square that divides into 8?
Yes.
4 does. So I can split that one again. So then I've got 2 times the square root of 4 times the square root of 2, right? And the square root of 4 becomes 2. And then 2 times 2 becomes 4. And then I'm done, right? Because no perfect square is going to divide evenly into 2. Now, how could we have made that a little simpler?
Find out the 16.
16, yeah. If we can find a bigger perfect square, what if we had said this instead? Square root of 32 breaks into the square root of 16 times the square root of 2. That's just 4 radical 2, right? So that would have been a little quicker, but they both work, right? That's how we simplify a radical, though. And this is a big number, right? I mean, paring that thing down is going to take a while. And we can either, Tim, you got a suggestion or idea? Yes, you may. So on this one, now I can take a couple different approaches. I could go through the kind of difficult task of trying to find a big perfect square that divides into 448, but that's not easy to do. 448 is a big number. Or I could just go through a whole bunch of little steps and take small perfect squares. Like, for example, I can see that 4 goes into that, right? 4 divides into 4 once, 4 once, and 8 twice. So I could split that up into the square root of 4 times the square root of 1, 1, 2, right? And then the square root of 4 is going to become a 2. Then I've got the square root of 112, and I could just keep going over and over again. But that's going to be a long process. Do you see why up here I didn't multiply that out in the original problem? Yeah.
That'd be really tricky.
Well, because now, look, yeah, this is, I would get that big number, 448, 16 times 28. This way, I've got 2 really small numbers that are easy to deal with, right? So I've already got this thing. This big number that I would otherwise have is already broken down into a product of 2 small manageable numbers, so leave it like that. Why screw it up? Let's leave it like that. So we can rewrite this then as the square root of 16 times the square root of 28, and the square root of 16 is just 4, and the square root of 28 can be broken up into, what's a perfect square that divides into 28? 7 and 4, because 4 is a perfect square, right? So I could make that the square root of 4 times the square root of 7, right?
Yep.
Square root of 4 is 2, so then this part just becomes, what, 8? 4 times the square, 4 times 2. And really quickly, we got this down to an answer, because the 7 we're stuck with. Okay, so that's actually really good advice that you use a lot in the future when you do simplify radicals. A lot in Algebra 2 next year. When you know you're going to take the square root of a product, don't make it a big number. Just take them individually in pieces, one at a time. Okay. All right. So geometric means you got those taken care of. I think that's it for that assignment. That's all there was with geometric means. So we can get rid of that one. Let's move on. I want to look real quickly at the first assignment from 8.3.
I got a very crappy grade on this one too.
Yeah, we can check. What about something like, say, I can't remember which. Oh, I know it was in the first page. Let's go back. Yeah, let's look at this first one. This is this simple. Let's look at this guy. So. You're correct. It is. But I want to talk about why. Because there could be some harder ones that aren't quite that easy to see.
Okay.
about this now? So the question is, what they want us to say here, first of all, they want us to write a similarity statement. That's easy to do. Let's get that out of the way real quick. If these were similar, what would the similarity statement be? LU, and it would be something like this. We'd say, you'd have to fill in the blanks. LUNR is similar to what?
CFQT.
Okay, CFQT. We got that. Because then we'd have to go L goes with C, U goes with F, etc. Right? So that part we got. But the bigger question here is, are they similar? How do we know?
Well, because L and U and C and F they overlap this way.
Okay, Andre, go ahead. Talk to
Okay,
us.
so if you put 6/4, it's a 3:2 ratio, and then 10/8, it's 5/4.
Okay, good. Now let's attach some terminology or vocabulary to that. Whenever we're doing it, and this is something, here's a rule of thumb, this will always work. When you're dealing with similarity problems, and you'll deal with a lot of those. This chapter is going to get, increasingly about similarity. Similarity problems, if two figures are similar, then the comparison of the two is always described by what's called a scale factor, which we've already talked about, right? So in this case, we have to come up with a scale factor for these. The scale factor is going to equal, like, let's compare what are some corresponding parts of these two rectangles, if they're similar, let's say. Okay, and more specifically, I guess what I'm looking for is,
L and U.
yeah, okay, good. Side LU would correspond to side CF, right?
Correct.
Those are scale versions of each other, if they're similar. So then, we could say that the scale factor equals either 6/4 or 4/6. Agreed? Okay. Now, it doesn't really honestly matter which one we pick. Usually it's implied that if this is the second one, then we started with the big one and ended with the small one, and so we'd make it 4/6 because things got smaller, right? But it doesn't really matter. All that matters is that I'm consistent. I'm going to say something like this. We're going to call this small measurements over large measurements. So in this case, we're going to set up the scale factor as the ratio of small to big. So if it's small to big, then that would be 4/6. Okay, so then if this is similar, that same scale factor needs to apply to all the pairs of corresponding parts. What's another pair of corresponding parts?
R and A,
Okay, say it again.
R, N,
True. Okay, those are also going to be
LR.
4 to 6.
L, R, and C, T.
Okay, good. So we got another one right here, don't we? We have LR goes with CT, and those numbers are 10 and 8. So if I'm doing the ratio of the small to the big, that would have to be 8 to 10, right? And the question is just, are those equal? And Hunter already told us they're not. And he went through the process of simplifying both of those fractions. If I simplify 4/6, it reduces to what?
2/3.
2/3, and 8/10 reduces to
5 halves.
Are you on track?
4/5.
4/5.
Yeah.
Okay, and those are not equal, right?
Not even close.
And so because those are not the same ratios, this is not proportional and it's not similar. Okay, but I got a potential issue for you to deal with here. That was a great way to do it. I like what Hunter did there. It made sense. But what if these numbers, instead of being nice 4s and 6s and 8 and 10s, what if they were square roots or decimals or something like that, where it was not easy to simplify them into fractions? What are some strategies I could do to check and see if they really are the same? Yeah. Okay, we could now, and I think what you're getting at, and this is a good idea. If we had a calculator, how could we always find out? Say it again.
Like divide them.
Yeah, divide them and make them decimals, right? I could turn this scale factor into some decimal answer, and I could turn this this ratio into some decimal answer, and that ratio into some decimal answers. And if the decimals are the same, then they're equal, right? What if I don't have a calculator though? There's another way we could maybe do this. If I want to check and this is kind of interesting. Let's see if you can come up with this. This is a good little trick. So we want to check to see if, once again, if 4/6 is equal to 8/10 without simplifying the fractions. Is there a property of proportions there that would be useful to us? Cross multiply, sure, right? Because don't we know that if we have a proportion, in other words, if both ratios are equal to each other, then the cross products must be equal. That's what cross multiplying does for us. So if I take these cross products, what is that cross product?
48.
48. Is 48 equal to, what's the blue
40.
cross product?
40.
It's not. And so we'd know right away that those ratios can't be equal. Another little trick. Okay. Yes, you may. All right, moving on. Moving on. Okay, I want to show you that these are bad questions. I don't like these. These were made, just disclaimer, these were made a couple of years ago. They snuck on here. I didn't look at them very closely when I put them on the assignment evidently because I really don't like these. I'm going to just delete them in the future. But they don't really make a lot of sense. I don't like the way they're worded. They won't be on the test. Maybe I'll change the wording and they'll be on the test. If triangle RAT is similar to triangle MUD, what is the answer that they're going for there?
That's like
M.
M. Okay, but that's not really a good way of saying it. The right answer is M, even though it's a poor question. What it should say is angle R corresponds to angle blank. That would be better, agreed? Because using that similarity sign right there doesn't really make sense. Angles aren't similar to each other. The angles would actually be congruent. Okay? And down here this should say segment RT corresponds to segment MD. Okay? So just know that those aren't very good questions. But I'm not going to change them.
that's another little 30. I did it now.
Okay, I think that's it for that one. I'm pretty sure it is. I'm pretty sure it is. Okay, let's look at last two.
Thank God.
Here's one of the new ones thrown at you.
Yeah, I don't.
Yeah, probably. I live on a quarter acre lot on the hill.
Let me show you. Yeah, you can read.
Yes, you
Not very big. Supposed to be lazy. It doesn't take really
I'm not gonna do it.
I have to work on this 5 days or 4 days. I'm judged.
Okay, so what about this one now? Real quick, take a look at this. You're going to get some. This is the easiest of the three. I'm going to tell you in advance here. The 8.3 part 3, the very short assignment. I'm telling you right now, I'm not going to help you with these. I don't want to walk you through these. I want you to get these. It's only 3 problems. They might take you a little while, but you got to get these now. So watch closely. Here's the example I'm going to give you that'll help you out. You may find it helpful to draw a picture. Yeah, you probably should draw a picture for this one. So here are our pictures. We're going to have 2 triangles that are similar. Let's make one of them bigger than the other. So here's going to be maybe the small one. And then here's one that's bigger but similar, supposedly. You get the idea. So now which one is, and don't spend time on the drawing making it fancy and trying to get it drawn to scale and all that stuff because it's completely irrelevant if it is. We don't care about that. The only thing the drawing is good for is just having a place to put some measurements so we can compare things and know which parts go with which parts. So we can see corresponding sides easily. That's it. All right, so then which of these 2 is bigger, first of all? Take a look at these.
The top one.
ABC is bigger, isn't it? Because we can see that for example, BC has a length of 40, right? Side BC has a length of 40. What's the corresponding side? Well, BC goes with EF, and EF is only 24. Okay? So we know that the big one is ABC. So let's fill that in. Let's call this ABC.
Yeah.
Yeah.
Are we done with this? You promise?
Yeah. still be as minus.
Raise your hand. I want to take a quick poll here. Raise your hand if this is, if it's not, I can deal with it. Is it annoying when people are talking in class? Raise your hand if it is. Okay, that's all I need to know. Okay, so if I fill in the blanks here, DE is 9. EF is 24. Obviously, I haven't drawn this to scale. It's not important. DF is 18. If I fill in the other parts on the big one, I just got to get the corresponding parts lining up. So AB goes with DE. So that's X minus 3. BC is 40. AC is Y minus 9. Okay, so now, if I want to, I want us to get this down to a really efficient process for solving for let's just solve for one of the variables. We'll solve for X. You guys can do Y on your own. How am I going to solve for X? I got to be able to set up a proportion to solve for X. So I want to start off with the scale factor. If I can write the scale factor for these two figures, then solving for X ought to be really easy. Say it again. Okay, so we're going to go ahead and do large over small. That's fine. We just have to decide which one are we going to do. So the scale factor in this case is large over small, and that is, would everybody agree that I've got to find, to get the scale factor, I have to find two corresponding parts that are both numbers. That's what I need, right? So I got a 40 and a 24. So large over small. 40 is large, 24 is smaller. So 40 over 24. Now I just have to fill in the blanks. I have to make an equation that's equal to on the other side. Let me rewrite this down here. How about 40 over 24 equals, I got to write a ratio with an X in it. So what's a corresponding pair of them? Okay, good. So this goes with that, right?
Yeah.
I got to go in the ratio of large over small. So which one goes on the top? X minus 3 over 9. And then I won't even finish it from there. How would I finish that problem?
Cross multiply.
Cross multiply, solve for X. Okay. Oops, don't need that. So then what about this guy right here? Last one. Then we're done. I'll let you guys just relax for a little bit here. So what about this? The perimeter of a parallelogram, ABCD, is 78. The perimeter of, and by the way, I forgot to write this, these are similar parallelograms. The other parallelogram, PQRS, has a perimeter of 15.6. And I've even got a drawing for you. Might be helpful to have a drawing, but there are my two parallelograms. I want to be able to find the lengths of the sides of the small parallelogram. Okay, so first of all, I guess the big one is ABCD, right? So let's call this ABCD. This one is QRS. Can I fill in any side lengths? What do I know any side lengths here? Yes, sir.
Side lengths A, B, and C are 14.
14, okay, good, 14 and 25. So the short and the long lengths in the big one are 14 and 25. Now I'm trying to find the lengths of the side lengths for the small parallelogram. So what can I call those?
X and Y.
X and Y, something like that. So this is maybe X and that's Y. I've got to come up with, though, a scale factor. And here's the trick in this problem. Here's where people had some trouble with this. Even if they knew how to do problems like the last one, people ran into a little bit of problem with this. Yes, sir? I can, and here's why. Either you had to do some reading or you had to really have paid attention in class. But you might remember me saying something like this. If you're comparing two figures, then the scale factor is the ratio of corresponding lengths, right? Corresponding side lengths, agreed? Okay, anything that you can measure in both figures with a ruler can act as a pair of corresponding parts. Do you measure perimeter with a ruler? You do. Any kind of combination of linear measurements is going to obey the scale factor just like a side length would. So I would measure, over here I would measure by, putting the ruler there and measuring 25, measuring 14, measuring 25, measuring 14, etc. That's a linear measurement. So I could use those for the scale factor. I could set up a ratio of, say, large over small. There's my scale factor. Large over small would equal, what were they, 78 and 15.6? Well, in terms of x, how could I set up that equal to a ratio involving an x?
25 over y.
I could do 25 over y, or if I'm solving for x, I would do
14 over x.
14 over x. Get it? Okay? And then I would just cross multiply and solve for x. Now, last issue though. On this problem, was this scale factor, that ratio, was that okay? I mean, would it give us an answer
Yeah.
that's correct? It would. It would work. Is it a simplified ratio? No. What if the question asks for a scale factor written as a simplified ratio? That's not going to work. I've got to somehow turn that 78 over 15.6 into a simplified ratio which has no decimals in it, right? It has to have integers. What do you think?
Could you times that by 10?
Yes, that's a great idea. Right? If I take this scale factor of 78 over 15.6, and I want to write that without decimals, the easiest way to get rid of a decimal is to multiply by a certain power of 10, probably the smallest power of 10 that works for me to get rid of the decimals. Well, on the bottom, if I want to turn 15.6 into an integer with no decimal, how many places do I have to move the decimal in that problem? Got to move it one. I got to move it over to the other side of the 6, and then it becomes a plain old even 156, right? I accomplish that. If I want to move the decimal one place, I'm just multiplying by 10 to the 1. I'm multiplying by a 1 followed by 1 0. Remember, the number of zeros that I multiply by, 1 followed by zeros. The number of zeros determines how many times I'm moving the decimal place. So if I just multiply through by 10 on the top and the bottom, on the bottom I get my 156. What do I get on the top? 780. Good. If I multiply, I'm just going to add a 0 there, right? Which is the same thing as moving that decimal over, but I got to add a 0 there to take that place. Is that my final answer? No, it's not. I'm not going to even bother getting the final answer. You guys can mess with that. But that at least is a starting place now. Those are both integers. What's the process I would go through to simplify that ratio? Yeah, divide them both by common things. Like I could divide them both by 2, for example, and probably have to keep going. But maybe I could divide them both by. Actually, I can't divide them by 4. 4 won't go in. Oh, will it? Yeah, of course it will. Of course it will. Yeah, I think it will. Yep, it will. You're right. So I could divide them both maybe by 4 to get a little head start, get another answer, see if I can keep working on that until finally I get down to some ratio that I can't simplify anymore. I can't reduce anymore. But at least I could start someplace here now. I got rid of the decimal. There's the missing step for some people. Make sense?
Yeah, boss.
All right. Okay. Good.
Can we watch that thing on YouTube now?
I have. Is it okay?
Yes.
You're 100%